that will give rise to a contradiction. Okay, if lambda I and lambda j are different, and yet if this is not equal to 0, I will have a contradiction. Okay, this means that if lambda I and lambda j are different, this must be 0. Okay, so we have this one conclusion that this must be true. That xi conjugate transpose yj must be orthogonal to each other. That if I and j are different, they have to be 0. That's one conclusion. Another conclusion, if xi equal yj, if I make yj equal xi, what do I have? I will have 0 equal to lambda I conjugate transpose lambda I. Okay, j becomes I. And then times xi conjugate transpose dot xi, because yj becomes xi. And this is magnitude square of this vector. It's a positive definite number. And this is equal to 0. This is not possible unless this is a real number. So that its conjugate transposes itself and it subtracts each other. So another conclusion that we draw is that lambda I must be equal to lambda I conjugate transpose, which means that lambda I is real. Okay? So just by that fact alone, if A is Hermitian, its eigenvalues have to be real, and all the eigenvectors that we have to be orthogonal to each other. Okay? So this is a very important fact. And they are also the concept of positive definiteness. If A is positive definite, if A is positive definite, means that lambda I is larger than 0 for all I. This is a mathematician notation, means that for all I. Okay? So what does positive definiteness mean? A is positive definite if you multiply by a vector b and then multiply by a vector b conjugate transpose. This quantity is always larger than or equal to 0, I suppose, positive definite, maybe just larger than 0. Okay, that quantity is always positive. And you can prove this property very easily by saying that B can always be expanded in terms of its eigenvectors. AI, say xi, I is equal to 1 to n. Okay? And xi being an eigenvector, and this is very much like Fourier series expansion that you have learned in other parts of the electrical engineering courses. How do we do this eigenvector expansion using orthogonality property? Okay, we know that xi dot xj is equal to c delta ij. This is true, and hence we can always find the ai's by just multiplying by, say, xj conjugate transpose dot b is equal to ai xj conjugate transpose dot xi. I is equal to 1 to n, but this becomes c delta ij. Okay, and then you can easily make the right hand side become ajc, just ajc. This might be a function of j as well. Okay, so you can solve for your aj, which is 1 over cj xj transpose dot b, and hence you can plug this in and prove this property very easily. I won't have the time to go through the proof, but this is true. Okay, so I guess I'll stop here, and just remember that understanding certain salient features of matrices are very important for quantum mechanics. It will appear over and over again. Quantum mechanics is also called matrix mechanics. I don't know how to teach quantum mechanics if you don't know matrix algebra. Okay, so I have to go through this. At least commit all these properties to memory. And then you will understand quantum mechanics later on. We will stop here. And again, we meet at 9 a.m. next Tuesday. Is that a good time? It's a good time, right? Then you can have a week off.